I'm going to talk about the temporal experiment for storms and tropical systems, technology demonstration mission. I'm the PI for the mission, and it's led by Colorado State University in Fort Collins, Colorado. We're about an hour drive from north of Boulder and Denver. And the CSU is leading the science part, led by Professor Chris Kumaro and Professor Chandrasekhar. And KPL is in charge of the instrument, led by project manager Todd Geyer and instrument manager Sharmila Padmanabhan, and many others. Then the spacecraft bus and integration of the payload, as well as mission operations and launch preparations, is handled by Blue Canyon Technologies, subcontract to CSU. They're in Boulder, Colorado. Our systems engineer is Matt Pallas, and Scott Palo, sorry we didn't list you here, has filed our FCC application and is working on the communications. So the mission is to perform temporally resolved measurements of clouds and their transition to precipitation on a global basis. So on the next slide here, we proposed to NASA Earth Venture Instrument 2. So that was the first NASA Earth Venture call. So Earth Venture was to transition from solely center-led missions to PI-led and cost-capped and schedule-driven missions. And that was the first opportunity for CubeSats, and it was expanded from 3U to 6U. And we applied in November 2013, proposed it. And so we were selected for technology demonstration, in-space technology demonstration, and we're managed by NASA Earth Science Technology Office. Our program manager is Bob Bauer. And so this was proposed as a low-risk, high-margin approach to use 6U class satellites for repeat pass millimeter wave radiometry. So you see here, we proposed 5 each 6U CubeSats to be deployed by the International Space Station and then separated using differential drag techniques. And each of those 5 would have a 5-frequency millimeter wave radiometer with the frequencies shown here, where they penetrate to different depths in the atmosphere due to a pressure broadening of the water vapor absorption line at 183 gigahertz. And so these would be flying 5 minutes apart, but that could be controlled, again, through the passive drag techniques. And so the point is to perform temporally resolved observations of clouds and transition to precipitation to improve weather and climate models, including cloud parameterization in global circulation models. And so the project started in August of 2015 with a 2-year development cycle. So we emphasize that compared to some of the larger NASA missions. And of course, that's more friendly for student timescales. And so we are delivering 1 complete flight system. We're constructing a spare as well to reduce the risk on launch. And we have an integrated payload, obviously, for launch integration in early autumn of this year. So we've been manifested by a CubeSat launch initiative under NASA Launch Services Program for launch on ELENA 23 in the 2nd quarter of the calendar year next year. So about April to June timeframe. We have to deliver this by no later than February 1st of 2018 to NanoRacks to integrate for commercial resupply service launch to the International Space Station. And then, of course, there's some waiting time depending on the astronauts and the airlock to deploy them into orbit. So the mission was designed for 5 6U class satellites and to observe at, say, 5-minute intervals as shown here. So this is a schematic with a growing storm that then starts precipitating between T+5 and T+10 here. The quality is not perfect here on the PDF, but the point here is that this row is infrared, and so infrared observations are available from geostationary orbit on something like a 5-minute time scale, getting higher time resolution. But so they give you the locations of the clouds, the morphology of the image from above, and the cloud top temperature. But what they don't give you is looking into the cloud. Due to the extinction in the cloud, they don't give you information about when precipitation starts. Whereas for millimeter wave radiometry here at 165 gigahertz, we get a large decrease due to scattering of the brightness temperatures, and you see that it's tens of Kelvin where the storm is happening. And the resolution of the lowest frequency or longest wavelength here is 25 kilometers, shown in the circle. So in addition to that signature, whoops, changing the slide here. There we go. So in addition to that, basically step function decrease at the onset of precipitation, as shown here on 165 gigahertz from a model, we also see the recovery. And so see if the 5 time samples are positioned here at every 5 minutes, then we'll see not only that step function, but also the recovery. And the recovery depends on the collection of supercooled water droplets on ice crystals, so some details of the atmospheric scientists appreciate very well. And so we looked at models of changing that so-called rhyming efficiency of the ice crystal growth from its baseline value to double and half, and we saw that we'd need a measurable difference of 4 Kelvin or greater. This is Kelvin in brightness temperature, and in 5 minutes. You know, from one satellite to the next, we need to be able to sense 4 Kelvin. And so our precision when comparing one satellite to another is 1 Kelvin in 5 minutes. And so we also, in addition to this constellation, we get additional information from the larger satellites when we have overlap in the orbits, for instance, NASA's CloudSat or ESA's EarthCare. So they both have 94 gigahertz radar observations that can provide additional information, as well as NASA's Global Precipitation mission. And so here we look at a one-year mission of Tempest. We look at data from AMSTER-E satellite radiometer data. So that and similar data has been available for well over a decade. And so we're looking at all rain events greater than 1 millimeter per hour precipitation rate over the globe, and from a deployment of Tempest constellation from the International Space Station at 400 kilometers altitude at 51.6 degrees inclination, initial orbit. Then in 1 year we'd have an overlap, we'd see with the constellation more than 3 million observations of precipitation all over the globe. So we're interested in a variety of climate regimes where the ground radar networks don't reach. And then out of those 3 million, 100,000 would be deep convection, and 50,000 would be overlap with NASA JAXA Global Precipitation mission. So you may be familiar that the microwave radiometers on that mission provide a lot more frequencies, and they provide the dual frequency precipitation radar. So with that, we can gain more information and sort of calibrate our measurements and learn a lot more. So our mission is a 90-day in-space technology demonstration after on-orbit checkout, and this is to reduce the risk, cost, and development times to deploy small satellite constellations, specifically 6U CubeSats, for Earth science measurements. In addition, it will raise the technology readiness level, TRL, from 6 to 9 of our millimeter wave radiometer instrument. It'll provide the first in-space technology demonstration, or first in-space demonstration of a millimeter wave radiometer based on, so this was jointly developed by Northrop Grumman and JPL, indium phosphide low noise amplifier front end. And these low noise amplifier chips are used from, produced by Northrop Grumman and designed in collaboration with JPL, as I mentioned. So this will be the first use of those LNAs for Earth science measurements. And so I talked about before, related to our success criteria, that we need to demonstrate feasibility of our differential drag maneuvers. So putting it from a low drag, which is an operational mode, into high drag mode, and then the orbit altitude reduces, the orbital period decreases, and then we do that one by one and move each satellite ahead, by the 5 minutes, and assuming they're all deployed at a similar time from, say, the International Space Station, for example. So that's one success criterion. The other success criterion is cross-calibration, or so-called radiometer intercalibration, which is being done by the GPM, NASA Global Precipitation Mission group, and it's been done for nearly a dozen years among the constellation members. But this would be the first CubeSat to do this and to do intercalibration between the Tempest millimeter wave radiometers and the GPM microwave imager, as well as the microwave humidity sounder on NOAA satellites and ESA UMET satellites. So there are 4 satellites in orbit operationally for MHS. And so in any case, we are cross-calibrating with 2 Kelvin precision and 4 Kelvin accuracy. So this is the brief overview of the 6U class bus called XB1 provided by BCT. And so this is the avionics module with the GPS antenna, star trackers, and everything that BCT provides. And then we add to that our UHF cadet radio provided by SDL and with a antenna design by BCT. And that's our primary satellite-to-ground communications link. Then we're using Globalstar as an important backup. So basically, the cadet radio will provide the bandwidth that we need for a continuous 10 kilobit per second payload data, as well as the satellite, the spacecraft telemetry health and state of health of the satellite. And so the Globalstar, if we don't have the UHF, the full bandwidth in the UHF passes. Oh, and the ground station is NASA Wallops for that. So then the Globalstar is our backup with a lower data rate, but we could get sufficient data to conduct our mission. And so this is a CAD of the instrument, and here's showing the hold down release mechanism by BCT to hold down these solar panels and deploy them in orbit. So we have a trifold horizontal array and a 45-degree canted solar array for battery charging. That hold down release mechanism also holds down a reflector. So more information about the instrument. Now the Tempest D instrument is a 5-frequency millimeter wave radiometer from 89 to 182 gigahertz. We have fairly wide bandwidths at the 2 lower frequencies, 4 gigahertz, and then narrower bandwidths closer to the water vapor absorption line of 2 gigahertz each. This is a direct detection radiometer. Won't go into great detail on that, but it avoids the local oscillator, it avoids any heterodyne, any mixing, and so that saves power, mass, and volume. So the spatial resolution of the footprint on the surface Earth's surface is 13 kilometers at the shortest wavelength or highest frequency, up to 25 kilometers at the longest wavelength or lowest frequency. And so the cross-track scanning is performed here. Some more detail on that. The observing profile, the radiometer views the Earth from nadir pointing to plus or minus 45 degrees, so over a 90-degree range, providing the 825 kilometer wide swath from a nominal altitude of 400 kilometers. And each pixel is sampled for 5 milliseconds. So this scan lasts 2 seconds, a mechanically scanned reflector, and it observes cosmic background radiation at 2.73 Kelvin, and the calibration target made by Zach's Millimeter Wave Corporation, where there's a lot of heritage for radiometer calibration. And so we see all those 3 within a 2-second period, so we can keep our calibration very well. So
Steve, 5 minutes.
Oh, thanks.
Sure.
We're getting just a few slides left. So in the build-up of the instrument, the bandpass filters were actually the end-to-end receiver response was measured, and this shows the 4 higher frequencies, not the 89 gigahertz, but so we show 4 gigahertz, 2, 2, and 2. So it met our specs for both center frequency and noise bandwidth. And then end-to-end testing of the flight model radiometer receivers showed that compared to our requirement here of this many Kelvin for the receiver noise temperature, we did about a factor of 2 better on 4 out of the 5 channels, and about a factor of 3 better on this one. So we definitely met the criteria, and we used the Y factor method with ambient temperature microwave absorber and liquid nitrogen for measuring those receiver noise temperatures at all 5 frequencies. And so the assembled instrument is shown here, integrated at JPL. This is ready for shipment to BCT that we did in April for the EMI compatibility test. And here's the scanning reflector. So the axis of rotation is vertical here. It's scanning to the left and right around this vertical axis. And the dual frequency feed horn is an example of a technology that was developed under ESTO, or Science Technology Office funding, starting in 2008. And Colorado State has been working with JPL on grants since then, to develop the technology. The front end here for the 4 higher frequencies is shown here with those low noise amplifiers that I discussed. Indium phosphide hemp, and basically the lowest noise temperature available in this frequency range. And then the power divider, basically a 1 to 4 way divider, but it also has amplification there to compensate for the insertion loss of the power divider and the filters. So the band definition filters are shown here, 4 of them. They're in waveguide, and then the detectors are shown here, 4 of them. And on the back side, the detectors are provided by Virginia Diodes, and on the back side of the module is also the video amplifier gain at low bandwidths to be able to have a large enough voltage signal to be transmitted here in these wires to the command and data handling CNDH module, where the analog to digital conversion is done, and the FPGA performs digital control of the whole entire instrument. And then the lowest frequency is shown here at 85. So basically, this dual frequency feed horn divides in waveguide, does frequency division, and the lowest frequency is front end, and detector is shown here. It also goes into the back end. So the instrument here passed vibration testing to NASA GEVS levels at JPL on the first week of June, and we did pre and post receiver testing. With that, today the flight instrument is in thermal vacuum chamber at JPL. It's a special new chamber for up to 6U CubeSats, and so we're looking forward to seeing results on that. So just a brief summary is that our mission is a 90-day technology demonstration mission after on-orbit checkout. It's to demonstrate the capability of 6U CubeSats to perform global observations of clouds and transition to precipitation, for repeat pass radiometry, to measure temporal signatures of clouds, precipitation, and storms. It performs the first in-space technology demonstration of indium phosphide hemp low NA front-end receivers for Earth science measurements, raises our TRL from 6 to 9, and demonstrates the feasibility of differential drag maneuvers as verified by GPS altitude, and doing cross-calibration with existing spaceborne assets to 2 Kelvin precision and 4 Kelvin accuracy. And we have a 2-year development cycle. We're delivering to NanoRacks this fall or launched ISS in about April to June timeframe of 2018. Thank you very much.
Thank you, Steve. A question for maybe John Carver or the Blue Canyon guys. What's the ConOps for the Globalstar TT&C for you guys? Or maybe to you, Steve. I don't know who can answer that.
Yeah, this is
Matt Ballas or John? Either one.
Yeah, this is Matt Ballas at Blue Canyon. We have some slides on the ConOps for Globalstar when we get to that section. We can talk about that there.
Okay. All right, so moving on. Is anyone from QBAR-RT online? I haven't seen a presentation from them yet.
This is Chris Ball. I sent a presentation to Charles. Was I supposed to send it to someone else?
Let's see it.
Yes, and I do have it here. I could forward it to Bruce.
Yeah, go ahead if you could do that.
I didn't receive any further guidance on where to send presentations.
Let's see. I thought I had it here.
Tell you what, let's do a chat question real quick for this presentation while we sort this out. we may have to jump ahead to the next presentation, but we'll come back to this one. So
Is there
go ahead.
someone I could email it to right now? Because I
Mike Miller was asking a question, sorry.
And yeah, Chris, okay, I see it.
Oh, here it comes.
I'll forward it to Bruce.
Gretchen, in the meantime, Mike.
Is Tempest D a federal mission or non-federal mission? And Steve actually responded in the chat saying it's a NASA technology demonstration mission.
Right. These are the.
Okay,
I think.
so we've since it's under control of a university, we've applied to the FCC for an experimental license.
So Charles, how does that go? They typically come back to us and look at the funding source, right, Mark?
Right. Is it who owns it? Who operates the satellite? Who does the satellite belong to? So
Hi,
even
this
if
is Pam.
Yeah, it's
I can answer that
complicated.
question.
Okay.
Yeah, this has been very confusing for a lot of folks involved, and we basically use grants to fund these. And under a grant, the PI owns it.
A good point.
So if you're on a grant and not a contract, and well, I don't know what the rules are for contracts, but on the grant, it's the funded institution, and there's been a lot of confusion because we might have academia or industry, for example, using wallops, and then they try and get an FCC license, and then it seems to cause all sorts of problems. So I've given the advice to a lot of the CubeSats that we have that are from academia that you really need to do FCC. And Bill, I've been in communication with Bill Horn extensively, and I guess I can just say now that he's looking at Qbert potentially as a special case because they're looking at radiation, and I haven't had a chance to close the loop with him yet, but my understanding is that Qbert is also going with an FCC license right now, even though they've got both Goddard and JPL involvement. So it's an area of it's a gray area. Let's just put it that way. And so we handle these things directly with the frequency spectrum management at the different centers as well as with Bill Horn to try and get on the best path that we can.
Hi, Pam.
Yeah.
Yeah, this is Scott Palo. It's my understanding that we're taking on ownership of the Qbert licensing through the FCC.
Okay,
Right.
but the grant, I think, is the key point there. That's a different kind of thing that we've done. Okay, so we're lacking the next two presentations, so I'm going to say, in the interest of time, let's jump to Tom. JPL, are you there? In the meantime, Charles will work out getting the other files from you guys here.
Yeah, I sent the Qbert presentation to you just now.
Let me just check one more time.
And Tom, because we fell far behind, had to step out for a moment, but he'll be back. So I'm not sure exactly when he'll be online.
Okay, well,
It should be within the next 15 minutes.
Yeah, so Bruce, what Tom were you referring to? Tom Johnson or?
sorry, Tom's Pagano.
And I'm afraid I have to sign off now to another meeting, but I will get back on when I can.
Okay. Well, Tom Johnson, if you're ready, maybe we'll jump to you because it's taking a while here to get through the wire to us.
Yeah, that's fine, and my presentation will be brief.
Okay, well, thanks for that. So we've got Halo set up, is that right?
That's correct.
Okay, so thanks, go ahead.
Yeah, so just as a real quick introduction, I didn't provide any science information, any background of the mission. I just concentrated on communications, so that's why the presentation is short. So you can go to the next page. So it's a 6U CubeSat. The PI is Phil Carrot from the University of Iowa, and the co-I is Keith Yehoda from Goddard. It's a CubeSat to study the hot galactic halo. We've got 3 X-ray detectors on it that are being developed by the University of Iowa. And there's 4U for the science instrument and 2U for the spacecraft. It's funded by NASA SMD. We went out, we did a competitive procurement and awarded the spacecraft to Blue Canyon Technologies. So I understand that Blue Canyon has a presentation that they'll get into more of the technical details about Globalstar, which we chose to use for HaloSat. So when we went out with our procurement, we had a requirement that specified both primary, which was specified to be UHF, and also a secondary, which was specified to be a space-based communication system. Next page. So the primary communication system, while we didn't specify it in the requirements, it was UHF. Cadet was selected primarily due to the high data rate. It's got a high data rate. It approaches 3 megabits, but in all practical purposes, it's a little bit over 2 megabits per second by the time you put all the packaging on it. We do have experience using cadets on prior Goddard missions. We're using it on 4 Goddard missions, supporting other NASA missions, as well as supporting NSF missions, going all the way back to DICE, which was 2 spacecraft that used the cadet. So cons of using UHF, this isn't just specific to the cadet, but really all UHF. And we've talked about some of this, but we certainly have to meet the NTIA and other regulatory requirements. They've got the experimental licenses that everybody's familiar with, government bans, et cetera. And then just meeting requirements such as the PFD on the ground is actually very challenging as well. So it can impact your comm link to the ground station. When you're using UHF, you're a secondary user, which means that if a primary comes in and takes your bandwidth or your frequency band, you have to find something else. You have to work around it. The spacecraft tracking can be challenging. So we use space track TLEs, which come from JSPOC. Occasionally, they do not update those. They typically update them on a daily basis. But we found that for spacecraft that are in low orbit, especially those that are released from the ISS, you have to have a TLE that's less than 2 days old to be able to track the spacecraft, and that's due to the narrow beam width of our high gain antenna. There are cases, just recently we've had a case where JSPOC did not update TLEs for over a week. So we were essentially in the dark for about 5 days. And I've heard of cases where it goes upwards of 2 weeks. So obviously having another way to get a TLE, get the location of the spacecraft would be advantageous. Also on cadets in particular, on 4 of the missions that we have underway at Goddard right now, we've experienced failures on 3 of the cadets. So obviously that's a high risk proposition. I know several other missions, MIT for one, that had issues with it. And then we had a problem getting product support from L3. L3 has since pulled out of the cadet business, and they've turned over operations and production to Space Dynamics Lab, and happy to say that support has improved on that, but it's certainly still a work in progress. So anyway, with all that said, it drove us to wanting a backup solution for all those reasons that I just mentioned. So we looked at secondary communication systems, and pretty much the first one that we looked at. Actually, I don't think we actually specified it in requirements, but Blue Canyon won the award for providing the spacecraft, and they were offering the Globalstar as a secondary communication system. It was relatively low cost, and it would certainly provide risk reduction if the primary system is not operational, or for blackouts either due to operations. You know, we have several cases where with the Wallops ground station, we operate during normal business hours. Actually, we've extended that some, but there are still periods where all the passes happen from midnight to 8 a.m. So you're essentially in a blackout period. So it would be good to have a secondary system. So that would provide increased coverage, and then also provides an additional means of tracking and communication, getting health and safety of the spacecraft and location. So cons, so I was happy to hear, especially the presentation by the AFRL, that it has been used successfully in many cases. So when we selected it, we didn't have any knowledge of its use, what missions had been used on, and the success rate. So it's good to hear some of that. And then also one of the cons is cost for data. Again, that's mostly due to just not being real familiar with it, but I do know that they've got different rates for when you're pulling data and what stations are used and so on and so forth. So, but that's something that I think we can certainly overcome, and it's more of a lack of knowledge than an issue, I would say. And so that's it. So I didn't provide detailed science information on the mission intentionally. And I also didn't provide detailed technical information about Globalstar and the implementation of it, because I did talk to Blue Canyon, and they assured me that they were going to be providing everybody that information. So they're open the floor to questions.
Well, I've got a quick question. So what is your requirement for your daily data quantity?
So it's whatever the spacecraft bus requires plus 3 megabits. So it's not a lot. It's a relatively low data requirement. So there again, it's